Hello, everyone. We're going to start on Module 9, which is Quantum Mechanical Theory of the Atom. So we are going to look at the behavior of electrons, the behavior of the very small, and we're going to take some of those atomic models like Dalton's atomic theory and the plum pudding model and the nuclear model. And what we're going to do is refine those using current understanding in the scientific community and go into a more detailed and more realistic view of what the atom actually looks like in today's world. So let me get started. Alrighty. So we are going to look at the quantum mechanical model of the atom. In early scientific history, in fact, not so early, as recently as the beginning of the 20th century, it was believed that all physical phenomena were deterministic. What that means is, if I throw a baseball and I know the angle and the velocity that it left my hand, I'm going to be able to determine pretty accurately where that baseball is going to hit the ground, right? In fact, this is sort of the idea behind pitching based on physical phenomenon associated with throwing the baseball. Pitchers can actually predict and physicists could actually calculate exactly where that baseball is going to end up and where it's going to pass the plate, right? Now, this was not found to be the case for things that were very, very small, like electrons. And no one really knew that until in the early 20th century, we had a ton of famous physicists determining that in atoms, the present condition does not determine the future condition, which means these particles were unpredictable. So they're indeterministic. So you've probably heard of a lot of these people. I mean, we've got Einstein, we've got Bohr. Maybe you guys haven't heard of de Broglie, but you will by the end of this module. We have Planck, we have Heisenberg, and that's the actual Heisenberg, not Walter White in the Breaking Bad series. We have Dirac, we have Schrodinger. So all of these people were really geniuses in this field of trying to take what was known and sort of rewrite all the rules for these subatomic, very, very, very small particles, because nothing that we knew at the time could explain how those particles, like electrons, behave. Now, it's really important for us to understand this idea of quantum mechanics because this forms the foundation of chemistry. It's going to explain the periodic table. It's going to look and explain the behavior of the elements in chemical bonding. Remember, bonding is due to valence electrons, which are outer shell electrons. Those electrons in those atoms are going to be the ones that are engaging and interacting and forming bonds. Quantum also provides a practical basis for lasers, computers, and countless other applications. So what we know is that electrons are incredibly small. If you think about this, a single speck of dust has more electrons than the number of people who have ever lived on Earth. We also know that electron behavior is going to determine the behavior of the atoms, bonding, what kind of properties it has. All of these different things are going to be explained if we can understand how electrons behave. We also know that when I directly observe electrons, something happens. The actual act of observing the electron changes its behavior. So directly observing electrons is impossible. The electron is so small that just the act of observing it, if I was shining a light on the electron, it would affect its behavior. Now this is quite a conundrum, because now we have to really think outside the box and try to figure out how I can write this new set of rules for these incredibly small particles. So the quantum mechanical model explains the manner in which electrons exist and behave. If I can understand this model, I'll be able to understand and predict the properties of atoms, because those atoms are, the behavior of the atoms are also directly related to the behavior of the electrons. So why are some elements metals and other are non-metals? Why does the atoms in group 1A form or lose one electron to form a positive charged ion? Why does chlorine gain an electron to form Cl minus? Why are some elements very reactive and others are basically inert, right? Why in other periodic patterns we see the properties of the elements? So what we're going to do is figure out what the new rules are for the behavior of electrons and other very small particles. In order to do this, we need to consider electromagnetic radiation. Light is a form of electromagnetic radiation. We know that electromagnetic radiation, or EMR, is composed of perpendicular oscillating waves. One is an electric field, one is a magnetic field. The electric field, in case you haven't had physics before, is a region where an electrically charged particle experiences a force. A magnetic field is a region where a magnetized particle experiences a force. One thing we do know about all electromagnetic waves is that they move through space at the same constant speed, which is the speed of light. This is a constant that you will be using frequently in this particular module. So I totally recommend that you remember this. It's also on your, this is one of the constants that is given to you on that conversion sheet that I allow you to use for tests. This is what these waves look like. If my direction of travel is in this direction, I can look at the red line. Now notice this is perpendicular, right? So this is a 90-degree angle. And in the red plane, I have those red waves, which are going up and down and up and down, centered about some 0. And that is the electrical field component. And then perpendicular to that, in the blue plane, I have the oscillating waves that are due to the magnetic field. So this is sort of what it looks like. What does electromagnetic look like as it's traveling through space? Now, the speed of energy transmission will be different when I have all kinds of other things in my atmosphere. My light is going to move at 3.00 times 10 to the 8th meters per second. Sound waves are a lot slower when they move through the atmosphere. So this is the idea of why anytime there's a lightning strike, I see the light and then there's a time lag and then I hear the thunder. The event causes the light and the sound at the same time, but the sound is going to be traveling at a much slower speed through the atmosphere, that the light is going to reach the viewer in much quicker than the sound does. Now, electromagnetic energy or light is that wave, right? If you've ever been to the beach and you see those waves that form and then roll into the beach, this is sort of familiar to you, but we're taking it into the context of that very, very, very small, right? So electromagnetic radiation, those waves, are characterized by wavelengths, frequencies, and amplitudes. So if I'm looking at a wave, the wavelength is going to be the distance between two peaks. I could also look at the distance between two troughs. What I need to do is look at one full wave, and then that distance is what I'm determining to be the wavelength. Now this is a lambda that I'm going to describe in terms of the wavelength. Frequency is if I measure the number of waves, the number of peaks, the number of waves that pass a given point per unit time, I'll get the frequency, which is nu, right? So I have lambda and I have nu. Nu is the frequency. The lambda units are going to be distance units, so meter or nanometer. My frequency units are going to be hertz or 1/seconds. Those are the types of units that I'm going to actually look at. Now the amplitude is this measurement here. It's the height of the wave maximum from the center. The bottom graphic is showing you that what we perceive as different kinds of electromagnetic energy are actually waves that have different wavelengths and frequency. So our visible light, for example, violet light, if I see something that has a wavelength of 400 nanometers and a frequency of 7.5 times 10 to the 14th seconds, reciprocal seconds, 1/seconds or hertz, that violet light in that visible light spectrum has this characteristic wavelength and frequency. If I look at infrared, that's a different, that's on a different part of the electromagnetic radiation spectrum. Remember, infrared is good for heat signatures, and it's not visible unless you use like infrared cameras or infrared goggles, that kind of thing. Notice it has a longer wavelength here my wavelength is going to be 800 nanometers, and my frequency is 3.71 times 10 to the minus 14. So I have an increased wavelength and I have a decreased frequency. And that should be a relationship that we know. Anytime wavelength increases, frequency decreases, because the product of that has to equal the speed of light. So, for waves traveling at the same speed, if they have shorter wavelengths, they have a higher frequency, right? The shorter the wavelength, the more frequently they're going to pass that given point in space. So wavelength and frequency are inversely proportional. Again, speed of light is constant, right? If I increase wavelength, I have to decrease frequency because the product of that has to equal the speed of light. If I decrease wavelength, I have to increase frequency because the product of that is equal to the speed of light. So here's an equation. Lambda nu is equal to c, which is the speed of light. So wavelength times frequency is equal to speed. If I measure the lambda in meters and I measure the wavelength in reciprocal seconds, 1/seconds, my speed is meters per second, which makes sense. It's distance per time, right? So C is defined to be the rate of travel of all electromagnetic energy in a vacuum, and it has a constant value, which is called the speed of light. So this, again, is something that we really need to pay attention to. And this is one of the first equations in this series that we also have to know. So here's an example. The light blue glow given off by mercury street lamps has a frequency of 6.88 times 10 to the 14th reciprocal seconds. That's second to the minus 1. It's 1/second, or hertz. What is the wavelength in nanometers? Notice my C is in meters per second, and I want my answer to be in nanometers. So when I do this, I have to convert my nanometers, or my meters, into nanometers, which is what this conversion does. But basically, I have lambda is equal to C over nu. This is my constant C. This is my given frequency. If I were to stop right there, my lambda would be in meters. So this is going to convert meters to nanometers. And what I get is an answer of 436 nanometers. So let's try this one. Here I have a lambda of 589 nanometers. And the frequency is what I'm looking for. If I use lambda nu is equal to C, I divide by lambda, what I get is nu is equal to C divided by lambda. This is equal to 3.00 times 10 to the 8th meters per second. To cancel out, my lambda has to be in meters. So one thing I can do is I can take my 589 nanometers. I know for every 1 meter, I have 10 to the 9th nanometers. And if I do that on my calculator, I get 5.89 times 10 to the minus 7 meters. So this is the value that I'm going to use for lambda. I get 5.89 times 10 to the minus 7 meters. Now notice the meters is going to cancel, so my units here are going to be 1/2 or hertz. So I know by using the units that I'm in the right ballpark. So I have 3e8 divided by that lambda, and what I get is 5.09 times 10 to the 14th hertz, or times 10 to the 14th 1/2, or second to the minus 1. Those are all going to be equivalent. So this isn't so bad. I can use this equation, the lambda nu equals c, in order to calculate various wavelengths and frequencies of the electromagnetic radiation that I'm interested in. Now, amplitude is a little bit different than wavelength and frequency. It's a little separate from that. The amplitude is going to affect brightness. So if I have a really short wave, my light is going to be dim. If I have a much larger amplitude, my light is going to be bright. So my different amplitudes result in different brightnesses. Different wavelengths actually result in different colors when I think of the visible spectrum. So if I look at this, red light is going to have a longer wavelength than yellow light, which is going to have a longer wavelength than blue. So this has an increased lambda. It's going to have a lower frequency. This one is going to have a decreased lambda. It's going to have a higher frequency. But the difference here is that when I have light that has different wavelengths, it's going to result in different colors as long as those wavelengths are part of the electromagnetic radiation spectrum that corresponds to visible light. So color is actually determined by wavelength and frequency. White light is a mixture of all of the colors of the visible spectrum. And you might remember these: red, orange, yellow, green, blue, indigo, violet. Those are all colors of visible light. When an object absorbs some of the wavelengths of white light and reflects others, it will appear to have a color. The observed color is predominantly the color that is reflected. So if I look at this girl, she's probably diligently doing her online chemistry work, right? At least she's not in her pajamas laying on the bed, there's nothing wrong with that. Sometimes I do that as well. You gotta work for your country, right? So look at this sort of rainbow of light. And if all those colors are hitting her shirt, many of them are going to be absorbed. But the red wavelength, right, the wavelength that has that corresponds to the red color of light is reflected. So that light enters your eyes, and your brain then registers the color red. And that's why you see that red shirt. The shirt is being hit with all of the colors of the rainbow, but it's also absorbing most of them except for the red wavelength. Now, visible light is only a very small fraction of all of the wavelengths of light. And all of these wavelengths are called the electromagnetic spectrum. If I have shorter wavelengths, I have higher energy. So I have another relationship. I decrease lambda, I increase frequency, I increase energy. So energy and wavelength are inversely proportional, and lambda and energy are directly proportional. Radio wave light has the lowest frequency. Those are those frequencies that actually, if you tune into AM or FM, you're going to have those really low energy, very long wavelength waves that carry that radio signal. High energy electromagnetic radiation is indicated by gamma rays. That has the shortest wavelength and it has the most energy. This high energy radiation is actually very damaging to biological molecules. It's called ionizing radiation. This is the type of radiation that can do a lot of cellular damage and a lot of damage to your DNA. UV light is high energy. That's why it can be so damaging to your skin and can actually cause cellular changes that result in skin cancers. So here's the spectrum. If you look at it, here's my visible wavelength. And then I've got sort of this blown up, usually between 380 and 780, about 400 to 800 nanometers is what I see in terms of visible light. All other frequencies and lambdas are outside of the visible range. So just to correlate, here's gamma rays, right? This is very high energy, and this is very low energy. Remember, as I increase lambda, I decrease, or as I increase frequency, I decrease lambda. Notice, here's the wavelength in meters. And if you think about this chart, I've corresponded some of the meters to sizes of different types of I don't know, objects. So atoms is on that 10 to the minus 10th meter scale. It's very, very, very small. Notice that viruses, like the coronavirus, is really, really small. That's why that virus can get through a lot of barriers, because it is so, so tiny that you have to, you know, those N95 masks are actually more effective at filtering out the virus, because that is able to handle things that are that small. Now, just as a public service announcement, masks are extremely effective in a large setting with a lot of people that are together in preventing transmission of the virus, because you do have a lot of virus that is encapsulated in droplets, that the droplets have multiple viruses in them, but they're a little bit larger, those droplets from a cough or a sneeze, and they can actually be effective at preventing your droplets from reaching other people. And now there is some scientific research that says there is some protection that you yourself are afforded against other people that have the virus, that is when you wear a mask. So mask wearing is actually, it should be mandatory, in my opinion. Okay, bacteria, they're a little bit larger. Dust, a pinhead, fingernails, all the way up to humans, which is, you know, now we're sort of in this macroscopic world. Right, you can see dust. At least you can see the dust in my house. because my dust is prevalent. I back to a cornfield, so my house is always full of dust. Anyway, so this is the spectrum. Remember, if I increase the frequency, I decrease the lambda. When I have short wavelengths, right, if I decrease lambda, I'm increasing energy. So when I have very small wavelengths, my energy is very high. Now, if I think about this, waves in that X-ray region have a length that is about the diameter of an atom, which is why when I study light, especially X-ray type of radiation, since they're comparable sizes, that's going to give me a lot of information about these atoms. So this is a prism. If my light comes in, this is all white light, and hits the prism will actually separate the light into various wavelengths. And on the other side of the prism, you're going to notice that you've got those beautiful rainbow, that beautiful rainbow of color. Now, it's kind of interesting because if you think about when you see a rainbow during a sun shower, all those little droplets of rain are actually acting as prisms, and that's what's separating the lights, and that's what happens when you see the rainbows in the skies under those conditions. All right. Let's talk about the properties of waves. One property of waves is interference. When two waves interact with each other, I can get something called interference. There are two types of interference that can occur. I can have constructive interference. So my waves actually add together to make a larger wave. And this has a special terminology to it. That means my wave is in phase. Or I can have destructive interference. So those two waves cancel each other out. And that would be called out of phase. So let's look at a picture. Here's my two waves. I have one up here and one down here. Notice that their peaks and their troughs are lining up, right? So those are called in phase. And if I add them together, basically, I'm going to get constructive interference, and I'm actually getting the same wavelength, but a much higher amplitude because these two waves are additive, and I get this constructive interference. Now notice, when this is at a peak, this is at a trough. So these waves are out of phase. They're like completely opposite of one another. You know, I have a trough here and a peak here. I have a peak here and a trough here. They're totally out of phase. And when I add them together, what I get is null. I have no wave. So those two waves actually cancel each other out. And that's what I call destructive interference. There's another property of waves, which is called diffraction. So let's think about a wave that's traveling along, and then it encounters an obstacle or some sort of an opening in a barrier. And let's say this slit that's in the barrier is about the same size as the wavelength. Waves will actually bend around that barrier. This is what is known as diffraction. Now, this is a characteristic of waves. Particles do not diffract. So waves will diffract, particles do not. If I have the diffraction of light through two slits that are separated by a distance comparable to the wavelength, I get an interference pattern of those diffracted waves. Now, this interference pattern is exhibited by all light waves. So it's a characteristic feature of all light waves because they act as waves. Here's an example. Here's my light source. Here's my wave that's traveling. Here's my two slits. So now my waves are bending, right? And the way these two waves that are resulting from that original wave can interact, I can have a dark spot or I can have a light spot. The dark spot is where I have destructive interference. The dark spot is where my waves are out of phase and basically cancel each other out. So there is no wave there, there's no light. The light spot is where I have constructive interference happening, right? The waves where I have constructive interference are additive. They're in phase and they make this bright spot. So what I get is this dark light, dark light, dark light, dark light, dark light. I get this very classic interference pattern, which indicates, like if I do this experiment and I get this interference, I say I have a wave and I can do a lot of calculations based on the actual diffraction. X-ray crystallography uses diffraction in order to figure out sizes of atoms and arrays of atoms in a crystal structure. So it's actually a pretty cool method. Now, light has those properties that we just talked about that are wave properties. They also have properties that are indicative of particles. We're going to discover that light and small particles have this wave particle duality. So let's look at evidence that shows the particle nature of light. One of those, one very classic experiment that indicates that light also can act as a particle is the photoelectric effect. So when I have a photoelectric effect, what happens is I irradiate a clean metal surface with light. That light causes electrons to be ejected from the metal. And I also know that the frequency of the light used for this irradiation must be above some threshold value. And that threshold value is actually different for every metal. So why? Many metals will emit electrons, right? Many metals will emit electrons when I shine a light on their surface. So they exhibit this photoelectric effect. Now, early classic wave theory, pre-quantum, attributed this effect to the energy in the light that's being shined onto their surface is being transferred to the electron. So if I look at classic waves, the wavelength of light is made shorter, or the light wave's intensity is made brighter, more electrons should be ejected, right? So if my light behaves according to classic wave theory. If I make the wavelength shorter, that's going to be higher energy. Or if the light wave is more intense, right, that's going to be brighter. More electrons should be ejected. Remember, this is because the energy of the wave is directly proportional to the amplitude and the frequency. This idea predicts that if I used a dim light, there would be a lag time before electrons were emitted. So if I didn't have enough energy initially, I would have to sort of accumulate more light. So I have to use more dim light, which would create a time. There's going to be a lag time before my electrons are emitted in order for them to absorb enough energy from that dim light in order to emit these electrons. So again, this is what is predicted by classic wave theory, pre-quantum. This is the experiment. I have light coming in, and then here's my metal. I have an evacuated chamber, so it's under a vacuum. This light now is causing these electrons to be emitted, and I can actually, based on the current that's generated, because these are a traveling line of electrons, right, I can figure out the energy and all of that good stuff. So here's the result of the experiment. When I plot the number of electrons ejected from a metal surface versus the frequency of light, right? So if I increase frequency, I'm decreasing lambda, and I'm increasing energy. So the energy of the light is increasing as this direction. What we find is there's a threshold value. Any light that is lower than this, that has an energy lower than this specific frequency, does not emit electrons, period. There's no lag time, it just doesn't emit the electrons. I do get, once I reach this frequency, if I use a lower intensity dimmer light, I will get fewer electrons emitted. So increasing the intensity of the light while keeping the frequency constant will increase the number of ejected electrons, because you are having more energy that is bombarding the surface. But it does not change the threshold value. So there's a certain minimum energy that must be present in order for these electrons to be emitted. So that goes against what classic physics actually predicted. There was no lag time. I could sit there all day and shine lower energy light and nothing happens. There is no lag time. They're not just sitting there accumulating energy. So Einstein was the one who proposed that light energy was delivered to atoms in packets, which are called quanta or photons. The energy of a photon of light is directly proportional to its frequency, and it's inversely proportional to its wavelength, right? Directly proportional to its frequency, inversely proportional to its wavelength. This proportionality constant is called Planck's constant, or H. And the value of Planck's constant is 6.626 times 10 to the minus 31st for joule times second. So this is joule seconds. So here's two new equations. The energy, and this is of one single photon, is equal to Planck's constant times the frequency of that photon. Now, because lambda nu is equal to c, because lambda is equal to c over nu, I can substitute this for my nu, and I have a different equation. Both of these equations are used in different purposes, but if you already know this equation, all you have to do is remember one of them and you can derive the other one. But these equations are used to calculate the energy of one photon of light. So let's get back to this photoelectric effect. One photon at the threshold frequency gives the electron just enough energy for it to escape the atom. So this is called the binding energy. When I have a shorter wavelength, remember, so this is an increased energy wave, that electron can absorb more energy than minimally necessary for it to escape. This excess energy that's absorbed actually becomes kinetic energy of that ejected photon. So I have another equation where the kinetic energy of an electron is equal to the energy of that single photon minus the binding energy for that particular metal. Energy is equal to h nu. So if I substitute that here, I end up with this equation. So this is to solve the kinetic energy of an electron. These binding energies are going to be variable and based on the metal that's actually doing the emitting of the electrons. So here's another fairly straightforward problem. Calculate the energy of a photon of red light that has a wavelength of 685 nanometers. So the wavelength is 685 nanometers. So I have lambda, so I'm going to use E equals hc over lambda. Remember, C is in meters per second. H is in joules per second. Lambda is in meters. So I have to convert this. I have 10 to the 9th nanometers in 1 meter. So what I get is 685 divided by 1 times 10 to the minus 9th, and I get 6.85 times 10 to the minus 7th meters. So that's the lambda I'm going to use. Now, I know H and I know C. H is 6.626 times 10 to the minus 34th joule seconds. C is 3.00 times 10 to the 8th meters per second. And now my lambda is 6.85 times 10 to the minus 7 meters. So meter cancels, second cancels. I'm left with joules, which is actually really good because joule is a unit of energy. Remember joules and calories. But we're in joules right now. So I take 6.626 EE minus 34 times 3 EE8, enter, divided by 6.85, second, enter, minus 7, and what I get is 2.90 times 10 to the minus 19th joules. So this is the energy in 1 photon of the red light. All right, the next section is going to talk about something different. So we are going to stop here, and I will come back shortly in order to continue our discussion on quantum mechanics. I'll see you in a bit.